Guess who's back? Back again. Shady's back. Tell a friend. Guess who's back? 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 Guess who's back?
Ladies and gentlemen, the subtle irony of a song is so appropriate at this point. I'm actually making this recording prior to my surgery, but at this time when you're watching this, my back will be fully reconstructed. I will be a new bionic teacher, so be prepared for January when I return. We have to finish up these 7/2 notes. Due to that little party you threw me, we fell a little behind, so we have to get through this. So we're going to talk a little bit about the law of large numbers and then do a couple of more examples using random variables to talk about means and standard deviations. So let's first talk about this idea of the law of large numbers. So when it comes to the law of large numbers with respect to expected values and averages for a random variable, what we're talking about here is looking at approaching the expected value e of x of a random variable over many trials for that average. So we've seen the law of large numbers before in terms of randomness, that something random will become predictable over a large amount of trials. But here we're talking about almost a calculus-related topic, that as x gets larger and larger and larger and larger, x being the number of trials, then the expected value should approach its true value for the distribution of the random variable x. So that's how we're using the law of large numbers in this setting. So in terms of going back to the original data that we were looking at for the AP Bio scores from 2012, I'm going to show the law of large numbers by using a graph here. And what you'll notice is over on the right-hand side, we have some individual observations for a couple of values for x. So trial 1 producing a value of 1, trial 2 producing a score of 4, and then a 5, and then a 2, and then a 4, and so on. And what we're going to do is just generate some means and plot some points and look at what's happening as the long-term trend starts to work itself out for the random variable x. So if you consider on the x-axis, the 1 through 9 is actually being sample sizes. So samples of size 1 through samples of size 9. And on the y-axis, if you consider these to be scores, we're going to look at what happens as the sample size increases when looking at the scores. So if I take observation number 1, it is the person got a 1. Ooh, that's horrible, but it happens. It's bio. I'm going to plot a point over here, the 0.11. And clearly there's no average because there's only one value, so I don't have to worry about an average. But the second person then gets a 4. And that means that the average has jumped up to a 2.5. Because 1 plus 4 is 5, divided by 2 is 2.5. So now, as the sample size has gone to 2, my running average has gone to 2.5. So I'll put a point here at approximately 2.5. By the way, this line here, this is my mu sub x line, and this is the 2.7 that we had determined earlier using that weighted average for the random variable. So now the next person gets a 5. Awesome. So that's 10 for trial 3. So that's a average score of 3.33. So now we're actually up over the expected average value for the random variable x. The next person gets a 2. So that's now 12, and 12 divided by 4 is 3. So the average has dropped down to a 3 after 4 trials. And then, we can continue this on. If we get a 4, the overall average is going to be a 3.2. So now at trial 5, we get a 3.2, which is again still above the 3.7. And you would expect that if we were to kind of look at this trend over time, it's going to start to kind of bounce around and approach this value of mu sub x. Now, I've kind of made my graph go a little quicker here. This is not really for the values of 6 through 9. There's probably a little bit more variance in there, but I think you get the picture that as x, the sample size gets larger and larger and larger, mu sub x should approach 2.7. Will it ever actually equal 2.7? Well, there'll be some variation. At times it probably could equal it exactly, but we know that that's what it's approaching. And that question for a law of large numbers example is, how large is large? What is the largest value that you need? And really all I can say at this point is that depends on variation in x. Depends on variation in x. The more variation in x that there is, the more trials you're going to need. The smaller the variation in x, the less trials you will need to see it approaching the true mu sub x value. All right, so let's take a look at something where we move away from a single mu sub x value, a single variable of that we're trying to represent, and build in a second variable. So we have one random variable x, which represents, in this example, the number of faded shirts that a factory produces in a given run, and the random variable y represents the number of jeans that are made without a button. Oh, the buttonless jeans, always a problem in my life. So just for the sake of this example, let's say that we know on average the company produces 42 faded shirts per run, and they produce on average only 87 jeans without buttons. That's a lot of buttonless jeans, but then again, no one really questions the content of a math example. So mu sub x is 42 and mu sub y is 87. If I wanted to combine these two random variables, so if I was interested in finding, say, mu sub x plus y, I think it's obvious to most of you that if you're combining two averages of two separate random variables, they would simply be mu sub x plus mu sub y. That there's no need to do any complicated math here, that the average of the sum of the random variables is the sum of their averages. So that's one of the known rules that you should know. It's very intuitive that that's how this would work. There's another thing that we can talk about in terms of the average value. So mu sub a plus bx. Let's say that there's a linear transformation applied to a single random variable x. So we know that some adjustment has been made in the manufacturing process, and now it yields a different output of the form a plus bx for the random variable x. So those new random variables are generated using this linear function. We know that mu sub a plus bx is going to generate mu sub a plus mu sub bx. Though we can split that transformation into the sum of each of those individual averages. But really, what is mu sub a? What is the average of a constant? Well, the average of a constant is just the constant. If you take a constant and add it up n times and then divide by n, you get the constant back. So mu sub a is just going to be a. And then mu sub bx, b is a scalar multiplier of x. So if you multiply an average by a scalar, or if you multiply every number in a data set by a scalar, it will change the average of that set by that scalar. So we can rewrite this as a plus b mu sub x. And I would challenge you guys on your own time, it's really hard with the limited time I have here on YouTube, to generate a random variable x, give it some distinct outcomes, and then go ahead and apply a linear transformation a plus bx, like 2 plus 3x, to the set and look at how it affects the expected value for x, and you should see that it should follow the rule a plus b mu x.